Hey folks, this is Frank, and in today's video we'll talk about AGI and how far away we are from it technically. I prepared a little presentation as a guidance and we'll start right into it. Of course, the reason I do this video is that current AI is very bad in terms of how much it understands the world around us. Real brains are much more powerful in many ways. In particular, they learn a predictive model of their initially unknown environment as babies, and somehow use it for abstract planning and reasoning. Also, humans have a sense of naive physics, which is the untrained human perception of basic physical phenomena, and also intuitive psychologics, enabling human empathy and innate emotions. There is research on how much of this is learned and how much of it is encoded in our genome. Check out this paper in Nature Communications that states much of this knowledge is innate, and artificial neural networks don't reflect such behaviors at all right now. Also, deep neural networks have a tendency to learn superficial statistical regularities in the dataset rather than high-level semantic abstractions, which is what humans do. All of this AI is narrow or weak AI in the sense that it is specified to handle a singular or limited task such as facial recognition, speech recognition, playing chess, you name it. These systems are mainly improved by three things right now: more data, larger models, and more amounts of compute. And in these narrow fields, they often outperform human performance. Now, these narrow fields are part of what Daniel Kahneman calls System 1 in his book Thinking Fast and Slow. The book describes two different ways in which the brain forms thoughts. There is System 1, representing fast, unconscious task solving, such as reading text on a billboard, localizing the source of a specific sound, or driving a car on an empty road. But then there's the interesting System 2, representing slow, conscious task solving, where you, for example, try to solve the task 11 times 17, actively think about a problem, or drive a car on a cold, rainy night in Stoke on a busy road. This System 2 is mostly unattainable for current artificial intelligence. There are a number of companies and research groups working on this, including but not limited to DeepMind, OpenAI, Mila, Facebook AI Research, and Google Brain. And they brought up some interesting ideas, and in this video I will talk about some of them in detail. So, what are the steps on the roadmap towards human-level AGI? For one, we need to get basics of System 2 going. Yoshua Bengio and Manfred Schölkopf argue that this requires at least two ingredients: attention and consciousness. Let's first talk about attention mechanisms. They are based on the commonsensical intuition that we attend to a certain part when processing a large amount of information. And they have been researched for quite a while now, starting with the work by Badanao and researchers from the University of Montreal in 2015. Since then, attention mechanisms have allowed huge progress in mostly NLP, but also vision. Broadly, they can be summarized as a vector of importance weights that lead to a model becoming specific to certain parts of the input. Attention mechanisms led to a revolution in neural machine translation, even up to this day, due to stuff like self-attention, hierarchical attention, and transformers. If you apply these concepts to vision, you end up at something like this, which reminds of human visual fixation, resulting in a point where vision is clearest. Now, attention in humans is very closely connected to the abstract theory of consciousness. Conscious thoughts are very low-dimensional objects compared to the full state of the brain, consisting of billions of neurons. Now, Yoshua Bengio argues in his paper, The Consciousness Prior, that the mere existence of such a low-dimensional conscious state, which is essentially an architectural and information processing constraint, forms a useful prior that may be necessary or even useful for computational models trying to emulate consciousness. So the idea here is to factorize knowledge into small exchangeable pieces. Technically, this can be modeled as a sparse factor graph, where a joint distribution over a high-level semantic concept is modeled. That means where the dependencies captured by each factor of the factor graph involve only very few variables, while still creating a strong dip in the overall loss function. Now, those factors that I just talked about are the things a conscious mind is thinking about and is aware of. The key is that this consciousness projection is a projection of a big vector, which is all the things conscious and unconscious in brain. And this vector is probably sparse. meaning that the conscious mind is only focusing on a few of them. Now, if such a selected item with a semantic meaning exists, it could be broadcast and stored into something like short-term memory, and there it could condition perception and action. In the end, this would lead to System 2-like sequential processing, conscious reasoning, planning, and imagination. Interestingly, this theory is in line with models of consciousness in neuroscience, the most important one being the global workspace theory, and it models the concept of working memory and is proposed to correspond to a momentarily active, subjectively experienced event in working memory, such as actively remembering a phone number. However, behind that is a gigantic set of unconscious processes such as longer-term memory, language, sensory inputs, operating in parallel with limited communication between them. But they can form coalitions which can act as input processes to the global workspace. The second large component for getting closer to AGI is a better out-of-distribution generalization, so that an intelligent agent can handle changes in distribution. I called this section from IID to OOD, independently identically distributed to out-of-distribution. All classical ML theory has been developed for IID data, and this includes that after deployment, distribution of test data in the real world has to match the original training distribution. This is not realistic, however, as many real-world distributions are non-stationary. That means they face changing places, times, sensors, actuators, and goals which can't possibly be learned offline, and also there are very unlikely so-called black swan events. Also, the common practice of shuffling data when training a neural network has been challenged, as it implicitly assumes data are IID, which is often wrong. In doing so, we destroy important information about changes in distribution that are inherent in the data we collect. As Leon Boutou says, nature does not shuffle the data, so we shouldn't either. But how do we attain agents who generalize beyond a training distribution? Well, on a very abstract level, the idea here is to consider relaxed assumptions, which is that the test data was generated under the same causal dynamics, but from different initial conditions, and which may be unlikely under the training distribution. For example, if humans learn how to drive a car in summer, they will still be able to do so in winter generally. Machines currently would have problems to do so, as they don't really generalize well to the underlying causal mechanics. But how do we attain that? Well, there are a number of ways. One way is to approach machine learning differently, so that the outcome of it is not a learned algorithm, but much rather a learning framework that is still able to adapt to new tasks. These general learners are then tested on simple benchmarks of different environments where you can easily quantify whether special high-level concepts have been learned or not. Papers on this topic include all literature on meta-learning, or learning to learn. Also, the recent search in transfer learning falls into this category. The most prominent idea there is model agnostic meta-learning for fast adaptation of deep neural networks from Stanford, where the idea is to adapt to new learning tasks fast and with few training examples. The specific idea here is interesting and rests on a quite intuitive optimization procedure. Given some model parameterized by f and some tasks and some data, you first perform standard gradient descent to attain a better set of parameters phi dash. Now, the meta-learning objective entails that in the next step, the original model parameters phi are optimized for the performance of f phi dash. In other words, we optimize phi as to attain a lower loss on the already optimized function f phi dash. The intuition behind this approach is that some internal representations are more transferable than others. For example, a neural network might learn internal features that are broadly applicable to all tasks in your set of tasks, rather than a single individual task. By training in such a way, you can encourage the emergence of such general purpose representations. There is a large strand of literature that builds upon this idea, and I will link it in the description. Another way to attain out-of-distribution generalization is a concept called compositionality. It is about how one might combine existing concepts in ways that may have zero probability under the training distribution, such as a frog on a scooter or greet the pink brontosaurus by the Ferris wheel. Note that this does not even have to be a novel pattern. It is simply one that may be unlikely under the kind of distributions that we've seen in the training data. Yet our brain is able to come up with these interpretations very easily. This dynamic recombination has caught some attention and is often also called systematic generalization. Of course, it's an open problem to transfer this to neural networks. In this context, remember the words of Charles Darwin. It is not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is most adaptable to change. One interesting paper utilizing compositionality is recurrent independent mechanisms, where the authors propose multiple independent recurrent cells that operate with nearly independent transition dynamics, communicating only sparingly through the bottleneck of attention, and they are only updated at time steps where they are most relevant. And this is very much in line with what compositionality is about. There are also methods that are based on a more explicit finding of causal structure in the form of recovery of causal graphs, a process which is called causal induction. For this to work, it's not enough to have observational data as usually, but you need data obtained through known or unknown interventions. For example, by targeting a certain variable, or when you don't know what variable is actually changed by an intervention, you can even target that, for example, with experiments. Another interesting approach for this is to deduct causal structure from interventional data by basically proposing some modularized architecture and then checking how fast a given learner adapts to new distributions arising from changes in these varied distributions. For example, you may propose a causal graph and then check whether it's correct by validating through data, basically. And these changes may arise from interventions, actions of agents, or other sources. In other words, they use the speed of adaptation to a modified distribution as a meta-learning objective. And this is a very interesting research idea. If you would like to read further and start implementing some stuff your own, I want to point you to some of the reasoning, abductive inference, and action learning benchmarks available. Another interesting tool is a new benchmark developed by François Chollet, the abstraction and reasoning corpus, which they call a psychometric intelligence test. Links to all of these are in the description. A good starting point for implementations towards this might also be the PyTorch meta library. A third major constituent is causality. Late last year, Bernard Schulkopf released a great article where he argues that the hard open problems of machine learning and AI are intrinsically related to causality, and he explains how the field is just beginning to understand them. It's a great read and rundown on basically 20 years of causality research, and I recommend reading it, but the essential takeaways are that current machine learning systems are based around an IID assumption and observational data, both of which are two strict assumptions, and in order to move away from that, machine learning needs to utilize methods based on interventional as well as counterfactual questions. Classically, such candidates are accurate physical models, structural causal models, and graphical models. He argues that there are a number of improvement axes for current ML systems. For one, traditional causal discovery and reasoning assumes that the units are random variables connected by a causal graph. Real-world observations, however, are usually not structured into those units to begin with, for example, objects and images. The emerging field of causal representation learning strives to learn these variables from data. Second, he emphasizes the importance to find transferable mechanisms, which already is a hot topic of today's research, and also to learn disentangled representations, which is very much in line with the modularity aspect that we already talked about. All in all, causality encourages to find a so-called interventional world model, which every human has built in, basically. I expect that going forward, causality will play a major role in taking representation learning to the next level, moving beyond the representation of statistical dependence structures towards models that support intervention, planning, and reasoning. Realizing Konrad Lorenz's notion of thinking as acting in an imagined space. This ultimately requires the ability to reflect back on one's actions and envision alternative scenarios, possibly necessitating the illusion of free will. The biological function of self-consciousness may be related to the need for a variable representing oneself in one's imagined space, and free will may then be a means to communicate about actions taken by that variable, crucial for social and cultural learning, a topic which has not yet entered the stage of machine learning research, although it is at the core of human intelligence. This again is somehow in line with the sparse factor graph that you already talked about, where there are very few variables which have a high semantic meaning, one of which may be a variable that represents yourself in an imagined space. Alright, I want to bring up some further ideas that might contribute to bringing us closer to an AGI, some of which are borrowed from the biological brains. First, I want to make another argument for modularity. Our brains consist of hundreds of different components on different hierarchical levels and with different functions, such as astrocytes controlling individual neurons, or subcortical components such as hippocampus and entorhinal cortex, without which we would not have our memories and it would be hard to orient in physical space. Thalamus, which filters data and relays it to the correct parts of the brain, amygdala that modulates responses to the input data, as well as claustrum that, when electrically stimulated, serves as the consciousness on-off switch. All of these indicate that intelligence life as we know it performs task delegation to some degree. Second is rethinking backpropagation. You know, the brain is highly modular and each of these modules consists of billions of neurons, but you only use a small portion of them at the time. Basically only those that are useful. Now, backpropagation uses all neurons at each iteration, which seems neither sensible nor very efficient. Nature is much smarter about this than utilizing the chain rule over and over. Next up is energy efficiency. Our brains are self-assembling biotechnology, and energy for running it was scarce for the better part of human history. Turns out that the brain is very energy efficient. When a result of unconscious mental processing is perceived as good enough, it is not bothering your consciousness at all. When you have an important task to do, a large-scale network called DMN, which is default mode network, is partially disabled and the central executive network is taking over. In contrast, deep learning utilizes all neurons all the time. That is why we don't have networks with such size. Besides, it is so energy inefficient that even processing units with operation frequencies counted in billions of hertz do not allow us to compete with the brain, which operates usually at just 10 to 40 hertz. Maybe we should come up with architectures that resemble this behavior and are not that wasteful. Fourth up is weight initialization. Neural networks are randomly initialized because gradient-based methods used to train them tend to break down when all values are 0, for example. Now in our brains it's different. We share similar semantic spaces from the very beginning. These regions are encoded in our DNA and shared amongst all humans, which hints that stuff like neuroevolution and pre-trained weights are correct ways of evolving current deep learning. My fifth point is digital neuromodulators. Human brains are strongly affected by chemical substances such as dopamine, serotonin, acetylcholine and histamine, called neuromodulators. Transferring this principle to deep learning, which would mean to auto-regulate some neurons, might be worthwhile. The sixth point is better hardware. Processing units for general purposes like CPUs are not as efficient as dedicated ones. To achieve efficiency required by complex cognitive architectures, we absolutely need much more parallelism. All that stuff I talked about may benefit from dedicated hardware. This would include devices such as FPGAs or ASICs. There are many companies that work in that field, so it will be interesting what kind of dedicated hardware will come out of this in the future. In the same line of work, there is neuromorphic computing. Essentially, neuromorphic computing entails developing analog neural networks, where network weights and activations are represented as continuous physical values, in particular diodes as activations and memristors as weights, as opposed to memory representations of floating point numbers. These systems may solve the fun These systems may solve the von Neumann bottleneck, describing the problem arising from the separation of memory and processing in today's deep learning. Moving the data back and forth between memory and compute units leads to performance degradation. Neuromorphic computing actually resembles the physics of neurons more closely and is orders of magnitude less energy consuming. I will link an article that describes this in more detail. Alright, summing up all this, how far are we from artificial general intelligence? The answer is hurtful and simple, quite far. We must acknowledge that in most regards we have not made a lot of leeway, and even though we can hope for huge progress in the near future, we are still very far from human performance in most regards. In general, in order to move towards more intelligent and more human-like artificial systems, lots of research indicates that we have to rethink our feedback signals, and that we should not measuring be skill, but rather skill acquisition efficiency, highlighted through scope, generalization difficulty, priors, and experience. Thanks for watching this video. If you like this content and would like to see more of it in the future, I invite you to like and subscribe this video right here. And until then, I wish you a very good time. Bye.